It turns out that even our best tech has an expiration date. Algorithms come and algorithms go. You don't buy that milk and leave it on the shelf for a month. It's not going to taste good. Treating your system's security as something you can set and forget is a prescription for disaster. In 1977, the DES encryption standard, or DES, was the undisputed gold standard of cryptography. Built under a government contract, it was universally adopted by public and private industry alike. But compute power grew. By 1998, a specialized machine called DeepCrack, combined with the processing cycles of thousands of ordinary desktop computers, broke DES in less than a single day using a brute force attack. RC4, another popular cipher deployed in 1987, suffered the same fate when it was proven broken 14 years later. And then a couple of years later, well, no, not a couple years later. It was a long time later that we finally got this one deprecated. It took years of exposure between the moment a system was proven broken and the time it was finally deprecated. The root of this problem lies in software engineering. So I embed the code to do the crypto right there. Everything's working fine until the day we find out that this crypto algorithm is broken. Well, I'm going to have to now go in, crack open the code in each one of these cases, and replace this vulnerable code. That's going to take us time. It's going to be error-prone. It could be that while I do that, I mess around and cause something else not to work. This is not ideal, and I've just shown you a very simple example. An organization may have tons of these actually in their infrastructure. Brittle, inflexible systems will collapse under the weight of new operating conditions. So what's the next thing on the horizon? What's the thing that's going to cause us to need to change all of this again? And the answer is, it's the quantum menace. This is the IBM Quantum System 1. Quantum computers possess the exact processing capabilities required to rapidly dismantle the complex math protecting our current digital security. For some defenses, the fix is relatively straightforward. Symmetric encryption algorithms like AES, which use the same key to lock and unlock data, can survive the quantum era by doubling their key size from 128 to 256 bits. But asymmetric encryption like RSA, which secures digital certificates, is different. A quantum computer's exponential power shatters the underlying math entirely. No matter how large you make an RSA key, it will still break. To secure these systems, organizations must write and implement new quantum-safe algorithms. The quantum threat is the catalyst exposing the flaw of hard-coded systems. Without overhauling how encryption is built into our software, the entire infrastructure will collapse under the weight of this forced migration. So, what's the answer to all of this churn? It's a thing called crypto agility. A better way is, instead of putting the crypto algorithms directly in the code, put it here and then make calls. This is a more modular approach. Instead of embedding encryption directly, applications make API calls to a centralized cryptographic hub. When a standard expires, a new post-quantum module locks into place at the hub. Every application instantly inherits the upgrade without touching its own code. The first step in this transition is generating a cryptographic bill of materials, or CBOM. You run deep system scans to map out all hidden legacy cryptographic dependencies across the entire network. That inventory tells you exactly where your vulnerabilities lie. But how does a massive enterprise execute this structural replacement while critical systems are still live and operating? Organizations use that cryptographic bill of materials to triage vulnerabilities, migrating the weakest, most critical systems first instead of patching everything in a single day. They rely on rigorous standards to guide that migration. This NIST laboratory helps evaluate and formalize the robust post-quantum algorithms massive networks will adopt. The goal of this migration is not merely to install quantum-safe algorithms. It is to install a framework that anticipates the need to change algorithms in the future. Global banking networks, healthcare databases, and government systems rely on this modular transition to prevent systemic data breaches and operational failure. Prioritizing a flexible migration framework over brute force patching is the only way large enterprises can outpace digital obsolescence without catastrophic downtime. In technology, change is the only constant. Relying on any static security measure guarantees eventual failure. True digital resilience comes from an infrastructure's capacity to adapt instantly to unforeseen threats. Modern security requires a shift from fixed encryption to adaptable frameworks. If you want to understand more about the technologies shaping our future, be sure to subscribe. Building systems with the assumption that every defense will eventually fail is how an organization ensures its infrastructure remains operational long after current standards have expired.